Hey guys, welcome back. So we're going to be talking about Virtual Lab 6 now, which is the reactions lab. And there were a couple of things that I wanted to point out to you guys in this particular experiment. So let's go ahead and take a look not only at Alex, where the lab is, but also at some notes that I'm going to give you for this. Okay, so share so that you can see what I'm talking about. That's always helpful. So again, this is the lab that talks about reactions. Okay, notice that there's some information over here in the before you begin, talking about double displacement reactions. Okay, when we talk about a double displacement reaction, what we're talking about is similar to the reaction between NaOH plus HCl, both of which are aqueous, meaning they're dissolved in water. And that gives me two products. And those two products are formed by taking the cation from this and the anion from this, and the cation from this and the anion from that. So do-si-do, we're going to trade the cations, trade the positive components. So I usually write NaCl because that was my first cation, and I put the other anion with it. And that's, again, going to be aqueous. Plus, and the other thing I get is HOH, which is a liquid, because that's water. Okay, so that's what we're looking at there. Now, I want to remind you that while we can write this in this way, there are other ways that we can write this, because we know that anything that's an aqueous component does not actually exist the way that it's written. So NaOH, when it goes into water, we symbolize that by putting the H2O over that arrow, becomes Na plus, which is then surrounded by water, and the OH minus, which is then surrounded by water. So they're no longer associated with each other. They're individual ions that exist in solution. Okay. The same thing is going to happen with the HCl. So when I put that into H2O, I'm still also going to get an H plus, which is aqueous, plus a Cl minus, which is aqueous. And of course, that's all happy stuff because everything's all still in solution. And the NaCl is going to be exactly the same because both of these components are aqueous. But one of the things that we find is that when the H and the OH get together, so this H and this OH come together, they actually come together and they don't fall apart that much, not very much. And that becomes liquid water. So because it's liquid, we write that as HOH. So if I were going to write this as an ionic equation, I would write this as Na plus aqueous plus OH minus aqueous plus H plus aqueous plus Cl minus aqueous goes to Na plus plus Cl minus plus H2O liquid. And I don't have to write it as the HOH. I can write it as H2O. Really doesn't matter how I write it at this point. There are certain reasons that we would write it in one way or versus another, but there's no real reason that you need to write it in any particular way for this class. Okay. Now, when we talk, and this is called, so this is called a molecular equation. And again, that's because we've shown everything as molecules, right? So cation and anion together, that's a molecule. When we talk about it this way, it's called an ionic equation because everything is shown in its ionic form as long as it's in an ionic form. Okay, so the Na plus, the OH minus, the H plus, the HCl minus, the Na plus over here, the Cl minus over here, and then that H2O, which is a liquid. We can also talk about a type of equation called the net ionic equation. And what we mean when we say that is that we want to talk about the things that do the interesting chemistry. So if I'm looking at what happens in this equation right here, so with the Na plus, the OH minus, the H plus, and the Cl minus, because that Na plus is aqueous on both sides, it hasn't done anything. There's no chemistry that it has done. And so it's just a spectator. It's just standing around watching the chemistry happen. So I can indicate that my Cl's are not part of that chemistry. But the H plus and the OH minus go to make this H2O. And so that's the interesting chemistry that I want to be able to talk about. Now, when we write our net ionic equation, we only include the things that have made something new and aren't in solution. Okay, so if we make a precipitate or a liquid or a gas, anything that's in a different phase, then that's what we're going to be talking about. Okay, and we only care about the things that were involved in that production. So I have my H plus, my OH minus, going to that H2O liquid. Now, does it matter if I write it as H plus and OH minus like I have here, or OH minus and H plus as I have it here? No, it doesn't. It absolutely doesn't. The reason that I have it the way that it is here is because that's what I started with. Okay? When I'm writing just the ions, it really doesn't matter how I write them. But what you'll notice is that I tend to put the positive ion, the cation, first, and then the anion, the negative ion, because in my head, that makes more sense. So that's just something that I do out of habit. It's not something you need to do. I don't care about that. As long as you get only the things that make the interesting chemistry. Okay, so that's the part we want to talk about. Now, when we're going into this experiment, so it talks about double displacement reactions. It talks about single displacement, okay, where we're taking one thing and putting, so this one is a molecule A, B, and C, and we replace the B with the A. So we have B and AC. That's a single displacement. Neutralization reactions are just like what we talked about here, okay? So that gives me an H2O. Neutralization reactions typically give me an H2O. Not always, but. And it says a table of solubility rules can be used to predict the insoluble products of precipitation reactions. Okay. Now, when we talk about that, we're going to go back to our content. And one of the things that you'll find in your exam handouts is solubility rules. It occurs in two ways in the ones that you have. Scrolling. So these are the rules themselves. And here's a solubility chart. Okay. So if we're looking at one of these rules, we'll say, okay, all common salts are group 1 elements. That means sodium, potassium, rubidium, cesium, francium, lithium, all those guys in that first row or first column are going to be soluble no matter what they're with. And stuff that's made with NH4 plus is also going to be soluble. Common nitrates, acetates, and chlorates are always soluble. So it doesn't matter what it's with, those are soluble. Okay. We can say that chlorides, bromides, and iodides are soluble except when they're with silver, lead, or mercury. Okay, and it's mercury 1, so Hg2 plus. Okay, not mercury 2, which is Hg2 plus. Okay, so the subscript is going on mercury 2. Okay, so those are some of the rules. Now, if those don't work for you, one of the ways that we can also talk about this is to say, okay, potassium is one of those group 1 metals, and so it's always going to be soluble. And if you look across this line, they're all soluble. Okay, if we look at the nitrates, which is said we're all going to be soluble, those are all soluble. Amazing, that's awesome. Okay, so that's typically what we see. Now, are there some exceptions to those rules? Yes, absolutely, because it says most acetates are soluble. This one is not. Okay, so understand that there are some exceptions to that. If you want to use this chart as opposed to these rules, that's perfectly fine. Why do we need that? Because we need to be able to predict what the solid is if a solid forms. Okay, so let's go look at what we're talking about here. And the reason that I want to bring this up is because a lot of students are confused about how you enter this. So it says to examine the appearance of each solution before mixing and record your observations in the lab data. To a clean test tube, add dropper full approximately 1 milliliter of each solution, observe the mixture, and check the temperature. So I want to mix the 3 molar sodium hydroxide, which is this guy right here. So I add that in there. And then 0.1 molar iron 3 chloride, which is this guy. I put that in there. And I put those back. Now I can check the temperature. Temperature hasn't changed. So what I can observe from looking at this in my lab data is that clear solution for now I have an observable change. I didn't form any bubbles. I didn't just change the color. It doesn't feel colder or hotter. So a solid formed, and I can actually see that solid. So this mucky stuff right here is solid formation. That's what that is. So that's why I choose the solid formation. And now the question becomes, what are the products that I would expect from this? So if I look at this, that's an interesting question, right? So let's go back and let's talk about what some of those things are going to look like. I'm going to pull this over so that we can look at our paper again. So I'm mixing NaOH plus FeCl3. Both of these are aqueous. Now, when I do my double displacement here, because I'm going to change partners, I'm going to end up with an Na. It goes, and of course, Na is a +1. And a Cl, which is a -1, so that becomes NaCl. There are no subscripts for that because both charges are the same. Okay. Now I know, based on these solubility rules that I was just looking at, that when I have Na and Cl, where's my Na? Na is, oh, there it is. Na is right here, and the Cl is right there, so that's soluble. So I would expect that to be aqueous, and it is. Awesome. And when I do the other thing, I have an Fe. And I can see over here that I have 3 minus because there are 3 negative ones. That means this Fe must be a +3. This is a +1, so that OH must be a -1. Okay, so I have my Fe. He's going to sit with that OH, but that OH only has a -1 charge, so I need to have 3 of them. Now, that means I've got all my charges balanced, and so those are the things that I would expect to put together. Okay, that's awesome. Now, I know that this has to be my solid. And why do I know that that has to be my solid? Well, okay. I see in this line right here, except for those in rule 1, carbonates, hydroxides, oxides, and phosphates are insoluble. Okay. And if I actually look down here and I see the Fe3+, not 2+, 3+, and I find that with the OH-, that's right here, and it says I, meaning insoluble. So that's my solid. Okay. Now the only other thing I have to worry about when I do this is that I need to make sure that this is balanced. Now, when I did this and I wrote my products over here, I have 3 hydroxides that I need. So that means I need 3 hydroxides over here. So I need to put a 3 in front of the NaOH. That's good because I have 3 Cl's here. So I need to have 3 of them there. And so now I have 3 Na, 3 Na, 3 OH, 3 OH, 3 Cl, 3 Cl, 1 Fe, and 1 Fe. So that is my balanced equation. Okay, awesome. Now, let me come back in here. I know that I'm looking for NaCl and FeOH3. NaCl is aqueous, so that's going to be that product. And then if I hit the control key on my keyboard, I can find FeOH3. That's a solid. So that's the other product that I'm looking for. Okay. And when I click off of that, then that's okay. So now I've gotten everything I needed from that. You need to do that for every single one of these that's in this list, right? And I know it's a long list, I get it. But when you do these things, you'll see what you're coming up with, okay? I will tell you that most of the reactions involving acids end up forming gases, okay? So I'm not going to say why, but I would expect this to make CO2. I would expect this to make SO2. I would expect this to make, actually, water. No. Anyway, I'm not going to talk through why I would do that. These are usually single displacement reactions. Okay, there is a solubility table here that you can use. All right, this is list-wise the same way that my other one was. Please understand, and this is something that comes up. The lists are not always the same. And the reason that they're not always the same is because we may have changed the way we designate something between soluble and insoluble in the time since one of them was published. So that may be, it may be that we know more about it. So that's one of the reasons that you might see that. It's very dependent on timing for those. So depending on how old a particular table is, that's what you'll see. It's just like if you look at old periodic tables, they don't have as many elements on them. And some of the masses are not known to as high a precision as they are now. Okay, so the age of your periodic table will also dictate things like that. While we're on that subject, whenever you're in ALEKS, make sure that you're using the stuff in ALEKS. I think I've already talked about this, but if you don't use what's in ALEKS, excuse me, it's going to freak out. All right. So make sure that you're choosing both of the products and that they're in the correct state. Okay. And make sure that you've noticed whatever change there is. All right. So if there's a change, make sure that you note it. Okay. I think that's everything I have to say about this particular experiment. That should take you through everything you need. If you run into questions, comments, problems, whatever, please let me know. I'll be happy to talk you through it. Thanks, guys.